Let's start our discussion by again considering the exact differential equation in this example that we have already solved by our standard method. And at that time we mentioned that there is another way of solving it, namely by the method of grouping. So let's see how this can be done. Okay, so without writing much, we straight away write the differential equation and then we group the terms. In what manner, that will be clear now. So what we do, we write 3x square dx separately, and from this second part 2y dy separately, and we group these two terms together, 4xy dx, 4xy dx and 2x square dy, 2x square dy. So then you notice that 3x square dx is just the differential of x cube, and these two grouped terms give us the differential of 2x square y. Well, the differential of this product is the differential of 2x square times y plus the differential of y times 2x square. Differential of y means dy times 2x square is 2x square dy, and differential of 2x square will be what? 4x dx, and with that we have the simple y, so 4xy dx. So that's how we get these two terms. And what is 2y dy? It's the differential of y square divided by 2, because differentiating y square will give you 2y. 2y divided by 2 is y times dy. So that's how you get this, which is equal to 0. And then this itself equals the differential of the sum of these functions by the properties of differential. So that is equal to 0, and 0 can be written as the differential of a constant, any constant. So C is the arbitrary constant here. And this is true if and only if this function is equal to constant. So that way, very easily you are actually getting the general solution. So you can see that instead of applying the standard method, what we did in the previous video to solve our equation, you can group the terms like this and get the solution very fast. The only problem is that it takes some observation and experience with differentials to be able to successfully do this, because there is no set rules for doing this. You have to see what works and you have to do that. Okay, so there is an arbitrariness in that. But this way also one can approach, although it's advised that when you are writing an exam and there you encounter a differential equation which turns out to be exact, you apply the standard method. Now to again see the two methods at work, we are going to see another example, the next one. Let's see. In this next example, example 2.6, we don't simply have a differential equation, but we actually have an initial value problem which we have to solve. So we have this differential equation and with that this initial condition also. So let us first apply the standard method and then we will do the method of grouping. So we start the solution by not really writing much. You can write whatever needs to be written. I am just going to go through the steps. So this is our m, 2x cos y plus 3x square y, and this is our n, x cube minus x square sin y minus y. So first of all we have to see if it is exact. So for that we apply the definition of exactness. So we calculate the partial derivative of m with respect to y. If you differentiate this partially with respect to y, x is considered constant and cos y will give you minus sin y. So that way you get minus 2x sin y. From this term you are going to get 3x square because y will give you 1. So minus 2x sin y plus 3x square. What will you get if you differentiate n with respect to x partially? This time y will be considered constant. So this term will give you 3x square, which you have here, and this term will give you minus 2x sin y. Remember that y is constant now. So that you have here, and that is why these two partial derivatives are equal actually at every point in the two-dimensional plane. But we only need equality in any rectangular domain, so we write, so the differential equation is exact in any rectangular domain D. In the plane you can write those things. And now because of this, what is the next step? The next step is to find a function f such that del f del x, that is the partial derivative of f with respect to x, is equal to m, and the partial derivative of f with respect to y is equal to n. So there actually the solution will start. So let's do that. So we seek a function f on D, again I am not writing those things, such that this is equal to m and this partial derivative is equal to n. So we are going to, as usual, start with this equation. We know what m is. M is 2x cos y plus 3x square y. Now to calculate f from this, we integrate both sides partially with respect to, integrate means partially obviously with respect to one variable, and that variable is x, because this is partial derivative with respect to x. So that means y is considered constant. Now if you integrate x, what will you get? X square divided by 2. After cancelling that 2 and this 2, you have x square, and with that we have cos y. Similarly, integrating x square will give you x cube divided by 3. So 3x square will become x cube, and y is there, plus an arbitrary function of y, because the integration with respect to is with respect to x. And then what we do, then we are going to use this second equation, and for that now we have to calculate del f del y from this expression, and then there we are going to use this value of n and see what we get. So we now use the value of n, which is this value means expression x cube minus x square sin y minus y, which is equal to n, and n should be equal to this. Okay, so we put that here, minus x square sin y plus x cube plus the derivative of phi with respect to y, phi prime of y. So you can see that these two terms cancel out, x cube cancel out, and that's how we get phi prime of y equal to minus y. Now this is a differential, ordinary differential equation involving only y, only the variable y. So if you integrate both sides with respect to y, you get phi of y equal to minus y square divided by 2. And do you remember that here it does not matter whether you write plus c or not. Ultimately, you are anyway going to get an arbitrary constant. If you consider an arbitrary constant here, that constant and the constant that you have in the general solution, they two can be merged together to give you a single arbitrary constant. So you can just simply use this value of phi of y where there is no constant, no arbitrary constant. So and then what do? We take this value of phi of y and put it here. So that way we get f, and f is equal to x square cos y plus x cube y minus y square divided by 2. So with this expression of f, what is the general solution? The general solution is that f is equal to an arbitrary constant. And then it does not stop there, of course, because we have to find the value of the arbitrary constant using our initial condition that is given to us, which was I think y of 0 equal to 2. So let's do that next. Hence the general solution is f equal to c, where c is an arbitrary constant, or this is equal to c. Okay, so that way this f is equal to c. You have to of course write where c is an arbitrary constant. I am not writing those things. But we also require that this initial condition be true. So that means whenever x is 0, y should be equal to 2. If you use this condition on this equation, what do you get? If you put x equal to 0, this term and this term vanish. And what happens here? when x is 0, y is 2. So that means minus 4 divided by 2 or minus 2. So C has to be minus 2 for this to be true. So you use that value here, and this is the solution to the initial value problem. So this is the solution to the IVP by the standard method. Now let's see the method of grouping. So this is the method of grouping. First we write the differential equation 2x cos y plus 3x square y dx plus x cube minus x square sin y minus y dy equal to 0. And then what we do? We group those terms together which have the trigonometric functions. You may understand why. Because when you differentiate cos y, you get minus sin y. From that observation, the idea of grouping these two together comes. We don't yet know whether it will work or not. Let's see. So 2x cos y dx minus x square sin y dy we keep together within brackets. And then what else should we do? Still we have terms having both x and y. One of them is 3x square y and the other one, well, this one actually does not have y, but if you multiply this with dy, then you can consider that product as having both x and y. But anyway, so what we do, we keep those terms and group them together. So that way we get 3x square y dx plus x cube dy, and that leaves us with this lone term minus y, and that can be kept separately because here we have minus y dy, so there is no x. Alright. Now if we note carefully, the first group is actually the differential of x square cos y. How? Well, what is the differential of x square? 2x dx. So that way we get 2x dx cos y plus, what is the differential of cos y? Minus sin y dy. So in this other term we have minus sin y dy, and with that we have x square. So yes, it is actually the differential of x square cos y, this part. Then here this group equals the differential of x cube y. The derivative of x cube is 3x square. Actually the differential, I should say, the differential of x cube is 3x square dx. And we have y with that, so 3x square y dx. And the differential of y of course is just dy. So that way we also have this term x cube dy. So this group really equals the differential of this. And minus y dy of course is the differential of y square divided by 2. There will be one intermediate line here, but I have skipped that because you saw another one. So that line of course will be differential of this plus this equal to differential of an arbitrary constant. And then when you lift the differentials, you get this equation. Is it the same equation? X square cos y plus x cube y minus y square divided by, well, not this one but this one, equal to C. So yes, you are getting that same general solution to our differential equation. And after that of course this procedure is same, there is no difference. So you will again get C equal to minus 2, and you will get that exact same solution to the IVP. So this is where this discussion ends. What we have next after this is this. You may encounter some equations. Actually we have already encountered one such equation when we were seeing the examples, which is not exact. But if we multiply that by something, then it becomes exact. And then that can be solved using our standard method or method of grouping. So the thing by which you multiply is called an integrating factor. Does it exist? In which case will integrating factors exist? using which you can turn a non-exact equation to an exact equation and then solve it. So we are going to see these things next week on this same day. So see you next week with these things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.